camera work here for a while. So I was going to say, first of all, yeah, I'm giving you guys till Friday to turn in homework. That won't always happen, but just it's the first homework, and we've had some people who kind of got here late, and so I'll make sure everybody has a chance to finish this one. So I'll give you another 2 days to work on the homework, but I'll collect it Friday. And then the next homework will be due Monday after that. So I try not to make them do so close together. It's just quirk of first 2 weeks with the Martin Luther King Day and everything. This upcoming Monday, there'll be another one that's due. But it's probably going to be more of the same. There's just like a lot of different algebra cases we got to deal with. Now, you had a question about the homework which is due. What was it? Problem 12C. Okay. I'm looking at it. So problem 12C, I give you this graph, and I asked you which points are limit points, list the isolated points, and find the limits at each left and right boundary point. So I suppose I have never defined left and right boundary point in class up to this point, so maybe I should do that. All right, so definition. Let's say, let U be a subset of the reals. Then 1, P is a left boundary point. And let me just draw kind of a picture of it to illustrate what I mean by that. So maybe U looks like this, right? I mean, I'm not sure. Excuse me. I think I got like a thread in my mouth or something from the mask. Anyway, P is a left boundary point. Means what it sounds like. It's on the left. It's like it's a left boundary point. So it would be something like this. Now, that's not the definition, right? What's the definition? P is a left boundary point. That's just a picture to try to explain to you where the definition comes from. If there exists delta greater than 0, such that, let's see here, P to P plus delta is a subset of the set. Left boundary point of U. So boundary points are always with respect to some given set. And 2, right, if the picture looked, and there might be all kinds of other stuff. Like, I mean, you might go over here and do this and that. I mean, whatever. It could have, U doesn't just have to be a finite line segment, it's just a picture, right? So here's another example. Maybe it looks like this. This could be P. That would be an example of a right boundary point. And like in, so P is right boundary point. If there exists delta greater than 0, such that P minus delta, comma P, is a subset of U. So these are special kinds of limit points. So like a limit point of a set is a point at which if you take like an open neighborhood around the point, open ball around the point, whatever radius you pick, there has to be infinitely many points in the set. So I think I realize now that that is not correct. It's not. This is the wrong. Not there exist. I'm an idiot. This is one of my. It's not. It's not that there's one delta, right? There has to be for all delta. No, that's not right. Son of a gun. No, it's there exists. I'm sorry. I have some wrinkle in my brain about this. I think there exists is okay here. But, and so like, here's a picture. That would be this, right? Right, so that's, what I'm trying to say is, in words, the left boundary point of a set is a point at which, to the right of that point, you have points in the set. All the points are in the set. Right?
So when you find the point of the limit at each vector, right, you have to write it like that?
Well, I mean, in practice, I don't think you have to actually, I mean, you could furnish the delta to prove your point, but I think as a common practice in here, we're just going to be like, that's a left boundary point, that's a right boundary point by inspection. But, for example, let's see here. So here's the graph, right? Not yet. Let's see here. Suppose that this one is at like -1, this one's at 1, this one's at 2, this one's at 3, right? Maybe this point right here is like, that hole in the graph is actually at -1, 3, right? This point right here, let's say, is at 2, comma, I don't know, 2.5. And this point right here is at 3, comma, 3. This guy right over here, let's suppose that that's 4, comma, 5. I don't know. Not to scale, obviously, right? I'm just... So, and what we're looking at here is y equals f of x, right? Okay. So then we can talk about isolated points, limit points, and left and right boundary points of the domain of f, right? Because we talk about things, we talk about limit point, well, limit point of a function would be the limit point of its domain, right? But to talk about left and right boundary points, we have to have some kind of set in mind, right? So the set I'm thinking of here is the domain of f. What is the domain of f? Well, let's see here. I can write it in interval notation. It goes from -1 over here to 1. 1 is included, right? Union, yeah. With what? With the set just containing 2. Mm-hmm. Yeah, 3. Oh, I'm an idiot. Listen, look at that. It's kind of scratchy down here. 3, 2, 4 included, right? So the domain is the allowed x values of the function, the inputs, right? So you guys tell me, what does it mean for a point to be an isolated point? It's by itself, right? That means that there exists a delta such that if you go plus or minus delta from the point, the only thing in that set is the point itself. Like that was our definition of isolated point, which I've never written on the board, but it's in the notes. And it is what it sounds like. It's isolated. So the isolated point here is 2. So I would be fine. I don't think you have to show work necessarily. If you wanted to give me a sentence that proves it, how would you prove that 2 is an isolated point? I would say observe, 1.5 to 2.5, which is equal to what? 2 minus 0.5, 2 plus 0.5, intersected with 2 contains only 2. So by the definition of isolated point, that proves that 2 is isolated. Because I could find a ball of radius. This is, in our notation, this is the ball, this is b sub 0.5 centered at 2. It's the ball of radius 0.5 with center 2. And the only thing that intersects the set U with, intersected with 2. I don't want to say intersected with 2. I'm dumb. What's supposed to go here? You guys are right. I need to drink more coffee. Not 2. That's dumb. Of course it just has 2 in it. 2 intersected with anything at most has 2. That's all it's got to offer. But what I should put there is U. It's an isolated point of U. U. So like this intersect U is just the set containing 2. That shows you that 2 is isolated. The fact that there exists some plus or minus, open set. But like Myron said, it's isolated. I mean, it means what it sounds like, actually. And I would argue left and right boundary point also mean what they sound like. The boundary is like it's an edge point, right? Which means that something's on the edge. If you go a little bit past it, you're outside the thing, right? So like a boundary point is one that it doesn't matter what radius ball you take around a boundary point. You have points both inside and outside the set. That's what makes it a boundary point. So left boundary point, right boundary point, these are specific subtypes of that. But part of the reason I've singled out left and right boundary points is, if we want to talk about a function's behavior, we're going to talk about the function's behavior in a different way if it's a point in the domain which is in the middle versus if it's a point in the domain which is at the edge, right? So this is going to become important. Like we want to have a language for this. We want to talk about, what happens at a left or a right boundary point. Now we have a notion for that. So can you tell me, what are the left boundary points? Of domain F here, yeah. -1 and what? And 3? Very good, yeah. It's a local concept. So like, you're like, but there's other things, but it can't be 3 because there's all this stuff that's what you're thinking, right?
No, I'm thinking it's for that one, -1 and 3. He's talking about the points.
Oh, no. The domain F. So we're just talking about the x values.
Oh, x values.
The x values. Yeah, so oh, that's a funny coincidence. -1.
That's why I thought it was the point.
And 3. Which is just coincidentally this. That's my luck.
So why is it 3?
3 is, so like both of these here, the proof is, if we look at, say, -1 comma -1 plus 1, right? That's -1, 0. That's a subset of the domain of F, right? And if I looked at like 3 comma 3 plus 0.5, for example, that's a subset of the domain F, right? The fact that you can look at that little, right, from 3 to 3.5 like here, and it just takes you to those. I mean, it's in the domain of F. That makes 3 a left boundary point because there exists a p to p plus delta, which is a subset of the domain. It has to be in that domain. Yeah. Well, yeah, I mean, if you can't find such a open set, then it's not a left boundary point. Like, for example, 2 is not a left boundary point. Because it's isolated, but more to the point, because I cannot pick. There is no, like, if you make delta big enough to get points in the domain except for 2, what happens? Like, you get over to 3, right? If I made delta equal to 1.5 about 2, if I went from 2 over to like, 3.5, then the thing is all these points in between are not in the domain, so it doesn't satisfy the subset condition. Like all the points to the right of a left boundary point have to be in the domain for it to be a left boundary point. That's what this means. All the points to the right of the boundary point, but close to it, close enough to it, are in the domain. It is a local idea.
Wait, are boundary points too?
Are what?
The boundary points too?
Left and right boundary points are boundary points. But 2 is also a boundary point.
Yeah, I still don't get how you got 3. I'm sorry. You say that all day for like that.
Which 3? Like this 3?
Yeah, the left boundary point. I don't know why it's 3. Like you just said all that. I don't get a single one.
Well,
Yeah, like I'm not. I thought I was the only one. I don't get it.
so, I mean, the x value here is 3, right?
Yeah.
So 3 is, well, it's not in the domain, right? But it's on the edge of the domain,
Well, that's the domain.
right?
It's in the domain.
You're just looking at X, right?
Yeah. So 3 to this, let me do it in green. This set right here, 3 to 3.5, that's of the form 3 comma 3 plus delta. That's a subset of the domain of F.
Well, why are we going to 3.5?
Just for example, like you can pick what, you gotta, it's up to your choice. There just has to be a delta such that that's a subset. So like, it's up to you to find the delta for a specific example. I just made 0.5 up because I know I can't go past 1 because I'm only over to 4 in this example we made up. So like all I've got to work with is 3 to 4.
That's the left boundary point. Why are we on the right side of the graph?
Because if it's a left fence post, that means that there's fence to the right of a left fence post, right? I mean, here's a fence post, right? If this is the left fence post, right? Then the fence is to the right of it. That's what it means, in fact, for a left fence, like a left fence post is a fence post such that there's fence to the right of it. No. So listen, like where did that 0.5 come from? I just made it up. I mean, you could just as well have used 3 to 3.1 or 3 to 3.05. The point is that there is some, if you get sufficiently close to the boundary point, you can find that as a subset of the domain. It's a local idea, right? Like if I took, over at this other one, if I took delta to be like, I don't know, 4, then if I went from -1 to -1 plus 4, that would be like this whole part of the number line, right? That's not a subset of the domain because there's pieces missing here and here, right? But if I shrink delta small enough, I can see that all the points close to -1, but to the right of it, are in the domain. That makes -1 a left boundary point.
So if there wasn't a gap between the graphs, would -1 be the only left boundary point?
Yes, if I could, like, he's asking if I suppose I, like that, then the only one.
So it's just because it's like a line, like they're like a line
It's
together.
separated, so you got 2 left boundary points.
That's right.
That-
Yeah. That helped? Okay, good. No, this is why I made this homework problem up, because like I can write these definitions down, but that doesn't mean we understand them, right? But I think if you understand this example, then you actually understand the definition. How about this? What's the right boundary points? That's actually a good check on us for this example. I heard right boundary points would be 1, 1, and 4. Right. And the evidence for that, if I wanted to give evidence, because maybe maybe it's a good idea to do it, would be like 1 minus 0.5, comma 1, which of course is 0.5, comma 1. That's a subset of the domain of F. You do not. No, you do not have to give evidence, but I'm just, like, we operate on definitions in here, so if it doesn't satisfy the definition, then it's not what it is, right? And like, so for 4, I could take, 3.5 to 4 as evidence that 4 is a right boundary point, right? So, and what's a limit point? I said a limit point, and this I did do. I did do this one in class, I believe. P in U is point such that there exists delta greater than 0 with P minus delta, P plus delta, which is just the ball of radius delta centered at P, is a subset of U. In other words, a limit point is a point where, actually that was not my, now I'm messing it up. That's one kind of limit point, but there's, the left and right boundary points are also limit points. Because my definition of limit point was more nuanced than that. That's a specific case of limit point. What I say is there are actually 3 different kinds of limit points. There are the ones that are in the middle, like case 3. They're the left boundary points and the right boundary points. Those are pretty much the 3 kinds of limit points at a finite point we're looking at. So, let's see here, I'm trying to find where I've, yeah, so if you look at definition 3.2.1 on page 103 of the notes, when you have a chance later, you'll see that I define limit point just to mean that limit point P, oh, P, and it's not, and I've already messed it up. Is P have to be an element of U? No. P in R is a point such that there exists delta greater than 0 with this intersect with U I still think I have it wrong. Oh, yes, I forgot. There's like a kind of an important point here. Curses. Uno momento. So what we want to do is go P minus delta, comma P, unioned with P, comma P plus delta. This is the deleted ball of radius delta centered at P, all right? Such, with this, I'm having grammatical problems here. With this having, not the greatest sentence, but here's the critical point. The deleted open ball centered at P intersect U is non-empty. So what this is saying in words is it's a limit point if when you intersect the open ball centered around the point, all right, and you ignore the point itself, there's something in the intersection. So like if this and this are both inside the set in question, then it's a limit point where you can approach the limit point from both sides. If just this is in the set in question, then you can do a right limit. If just this is in the limit point, you can approach from the left, right? So left boundary points allow getting to the point, the kind of limit we can set up for this one is x goes to p in what sense? And this one allows us to set, I'm going to put this as kind of parenthetical comment here, x goes to p in what sense? For approaching x like that, we put a little plus up here for that kind of limit. We put a little minus up here for this kind of limit. So we take a right limit to a right boundary point. We take a left limit, excuse me. We take a right limit to a left boundary point because we're approaching from the right. We take a left limit to a right boundary point because we're approaching from the left. I'm sorry about the double-handedness of the terminology. It's just the way it is. You know? No, it's good. These are good questions. On the other hand, if you actually have both of these being non-empty, right? If these are both non-empty, that sort of limit point allows us to calculate the so-called double-sided limit, right? The double-sided limit. In other words, just x goes to p. That's the kind of limit we can calculate at such a point of that. So that's all. Now, the other part of the question was to calculate the limit of this function in that homework problem at each left or right boundary point, right? Number 12, yeah.
It just said find the limit at each left and right boundary point.
Oh. So, sure, but that's when I calculate, find, for me, it's the same thing, but yes, yeah, okay. Like, the calculation here is just to look at the picture.
Oh, okay.
You know, I mean, for that homework problem. But for this problem on the board, we can do it, right? Like, so this is useful. This is a great example, actually. There's so much to learn in here. How about this? So we would write the limit as x approaches minus 1, right, of f of x, because we don't even have a formula. All we got is a name for it and this picture. Now, it's going to what? It's going to 3, right? So it's going to be equal to 3, because that's where the outputs are settling. And I'm not done yet, right? This is not a double-sided limit. We can't even approach from the left, right? We're just approaching from the right. And so we do what? We do a plus right here. That's our notation, because we're just approaching from the positive side of the limit point. That is true. That's a theorem. The double-sided limit exists if and only if both the left and right limits exist and agree. If they both exist and don't agree, then the limit doesn't exist. And we call that kind of point a finite jump discontinuity. We'll talk more about continuity here before too long, but we're not quite there. But so how about this one? Limit is what? X approaches 1, f of x equal to what? I guess I didn't really tell you what that point was. So you guys tell me what the point is. So this is, 1, 2. That seems reasonable. 1, 2. So if that is 1, 2, then this is 2 here. It's debatable. My graph is not the scale, right? So thankfully the homework I made with a, software, so it's less ambiguous. And then what should I put on the 1 here? Because we're coming from the left of the limit point, so we put a minus right there. Because we're coming from the right of the limit. So this is a right limit, this is a left limit. Like that. Like that. The left and the right is, it refers to the values, not the direction of the limiting process itself. But approaching from the right You don't really,
It's furthest from the right, so it's a right limit.
yeah, I mean,
If it's left,
yeah,
furthest left, the furthest from the left is a left limit, moving towards the right.
yeah. If I'm not careful, I'll mess it up. But that's why this notation is great, because it frees us of trying to make sure we've got the right preposition and word order. Like, thankfully, we live in a world with notation, right? We don't have to write prose sentences to explain algebra. Like, you read what mathematicians, how they expressed equations before they had algebra. It's truly horrible. Like, thankfully, we have notation. So this means we're looking at values a little bit to the right of the limit point, right? I mean, that means that you can consider x is equal to like -1 plus some little delta in this limiting process. That's the way you think about it. This one, we're looking at values like 1 minus a little delta in that limiting process. That's the distinction. And the limit, how about this one? Did I answer your question accidentally? You had a question. What was your question before I blather on?
When we given the limit, like for example, limit to x to like
Limit of what? X
1 plus,
1 plus, yeah?
and if you given a value in front of it, let's say this theta, no, just put a number that would, you know,
Number in here or
yeah,
3?
Let's say 3.5.
That's a good number, I like
you,
that number.
yeah. That's like you say, you put x, let's say x minus 3. Let's say so.
Okay.
Now, do we have to add the, like, do we have to substitute the x, the limit of x is equal to 1 to the x minus 3 of
Sure. This kind of limit, with the limit laws, we just plug in the 1 and we go 1 minus 3. So we get -2. So, so like I had a theorem I told you guys last time, which is that if we have a polynomial and we take the limit as x goes to a of a polynomial, we get p of a. Like, a polynomial is almost anything, so many things you think of. I mean, it's any expression of the form a(n) x to the n plus a2x squared plus a1x plus a sub 0, right?
I was confused there, but I got it.
Pythagorean. No, not so much. My point is, let me, this is not helpful to you. So the limit laws I wrote down last time, I wrote them for double-sided limits, right? Like, limit as x goes to a. But because what she was reminding me of, the double-sided limit exists only if the left and the right limits both exist separately and are equal to that double-sided limit. So every theorem I wrote down for double-sided limits is also true for single-sided limits. Like a polynomial, if we have the limit of a polynomial, this is a polynomial of a kind of stupid sort. It's a first-order polynomial. And because that formula makes sense at 1, I can just plug in 1, and that calculates the limit. Sure. Do you guys want me to do the remaining 2 limits here, or are we good? I think we should move on to some more like algebraically challenging problems, yeah? Is that helpful? So the reason I made the first question in your homework to read the notes, I did, right? That's because that's the first thing you want to do is like become aware of what's there, what resources are there, because sometimes, especially the harder problems in the homework, there's a good chance that it's just almost a literal, like just slight twist of something that's already in the notes. For example, I asked you to prove the sum rule for limits, right? That proof is verbatim in the notes, so you can just copy it. I really just want you to copy it. The process of copying the proof will help you understand it, actually. And so that's what I want there. And, you know, you don't have to read the notes super carefully. I just want you to at least scan through them so that when you have a homework problem, you can zoom in on the part which is most interesting and helpful to you. So, yeah, I should be reposting the notes this afternoon. I've just finished editing them, like past the point I've posted already, so I will have the complete set of notes posted pretty soon. I've tried to remove all references to like my previous teaching or course numbering where I was teaching at Liberty. So if in your reading you happen upon something like me talking about Math 225 or something like that in the notes, let me know about it so I can get rid of it, because I'm trying to make them more, you know, tailored just for here. But it's a process, right? Anyway, that's just a comment. But the other thing about the notes is, like, let's take this question today about left boundary point, for instance. You know, one of the things you can do as you're faced with a question like that is, my notes are a PDF, right? So I think if you just use Adobe or something, you can like search for the words left boundary point, and it should find in the notes where that is. So you can use the search feature because I give you a PDF for the notes. Like, that's helpful. I have not created an index. You know, eventually I'll get to that. But who needs an index when you've got a searchable PDF either? So, excuse me. All right, so let's just try to hit a bunch of examples. And I'll try to do a variety of things here. Start out with one more graphical one. All right, so let me just, what I've given here is a graph of a function, right? And now I'm going to just write down some limits that I can tell you from the graph, all right? So the limit, and so I'm going to start from the left of the graph and kind of work my way to the right, saying whatever I think I can say in an interesting way, all right? So first of all, the limit as x approaches minus 2 from the right of f of x equals 2. You guys fill in the blank for me. By the way, this is like a pretty typical test question on your first test. Like something like this, it tells me a lot about whether or not you've understood the concept of a limit. I like this for a question because you know, if you're completely lost in terms of algebraic simplification, right? If such an injustice has been done to you in your previous math classes that you don't know how to factor or whatever, you can still get this problem right? So hopefully. So you guys, help me out here. What's the answer to the first one? -1. Very good. Because we're approaching -1 there. So the value of the limit refers to the y up, the y values in the graph, right? The outputs. The limit point is the inputs, the x point. So I try to distinguish between limiting value, which is the number which the functions get close to, the outputs of the function get close to at the limit point, whereas the limit point is the input. But anyway, x approaches 1 from the left is what? It's 1. Approaching from the left, we can get as large as we like at that vertical asymptote. It's infinity, right? Limit as x approaches 1 from the right would be 1. Very good. Limit as x approaches 4 from the left. Excuse me, from the left is a problem for me. X approaches 4 with an upper minus. There we go. It's the top one, right? 2. Remember, the value refers to the y, not the x. The limit point here is 4. How about x approaches 4 from the right? I guess I didn't really make it clear. Let's say that that's 4 comma 0.6, I don't know, whatever. So then 0.6, yeah. Exactly, this one does not exist. Dead on arrival here. Now technically, the one that's infinity also does not exist. But this is a better description of how it's failing to exist, you know. At x equal to 1, we have a vertical asymptote. At x equal to 4, we have a finite jump discontinuity. All right? Let's see here. Let's look at some limits. So here I'm supposed to find the limit or explain why it does not exist. For what it's worth, this is Thomas's Calculus, the 14th edition. 14 editions. Why do you have 14 editions of a calculus book? Because it's hard to charge $300 for a book that everybody already has. But if you make a new edition, then they're rare. But I don't know. I like Thomas's Calculus. It's a pretty good book. Stewart's also good. Anton's good. There's like a lot of good. You should have something so that you can open up and because I'm going to give you homework to turn in, right? And if you do those and carefully understand them, you'll be pretty good, right? But if you want to be really good, you need to do additional problems, right? So it would be wise to have something that you could work additional practice problems in if you want to. Now, I have solutions posted to problems from, I think, Stewart's Calculus, I want to say 6th or 5th edition on my website. I've got 40 PDFs with something like a dozen problems from each section posted. So if you get that one, you can look at my solutions to that book if you want. That is sufficiently, I think Stewart's in its 7th or 8th, who knows, edition right now. I don't know. Stewart is no longer with us. He passed on, but they still keep making new additions to his book. And I think anyway. But anyway, you could probably get that old edition of Stewart for pretty cheap if you wanted to use my solutions in that regard. All right, well, enough about that. Let's look at this problem here. Start out with a relatively easy one. Limit as x approaches 0 of x squared minus 4x plus 4 divided by x cubed plus 5x squared minus 14x. So what's the first thing we try to do? Yeah, plug in 0, right? Yeah. Do you see the problem?
I can't think of a factor.
Factor. Yeah, well, oh, yeah, that's true. We could factor, but
You plug in, you realize the zeros on the bottom.
yeah, if you just look at the bottom, there's no constant term, right? So when we plug in 0, this is 0, so we've got division by 0. But when we plug in 0 onto the top, we get 4. So it's 4 over 0. This means that the limit doesn't exist. For the limit to work out, to exist, we would need there to be an indeterminate form. This does not have an indeterminate form. It's just something finite over 0. That just blows up. Now, we could ask the question, does it go to infinity? Because it minus infinity, right? My intuition here is that this one's going to go to infinity on one side, and it's going to go to minus infinity on the other. So the answer is going to be does not exist. I mean, you could try plugging in, if you try plugging in like 0.01, for example, try plugging in 0.01. If we plug in 0.01, let me call this thing altogether f of x. So if you think about f of 0.01, you can see that it's approximately 4 over, minus 0.14. Because x cubed and x squared and x upstairs, like these two last terms are the dominant things if x is super tiny. So essentially the value is governed by that. So you can see that that is negative, right? That's going to be less than 0. And you can make that as, of course that's a large negative number, right? And you can make it larger and more negative if you take like 0.001 or 0.0001 and so forth and so on. So from this, I can cipher that the limit as x goes to 0 from the, what is that, from the right of this expression, which is what, a rational function, right? Is infinity. And I think on the flip side, if I was to look at this junk, if I was to look at, I forgot to throw the ones out from yesterday. They're still getting me. The negative of that, what would happen? It's like 4 over 0.14. Those are the dominant terms, And so you can see that's greater than 0, and it's a large number. And we can make it more and more large by taking that to be closer and closer to 0 from the left. I mean, the values to the left. So the limit as x approaches 0 from the left of this thing is what? Negative infinity. So in this context, what do we say? We say that this does not exist. Right. You might be tempted to write plus or minus infinity, but we don't write that. All right, so sometimes that's what happens. Sometimes they just blow up, right? That can happen. What would happen if we replace this instead of a 0 with a 2? Then maybe we can do the factoring you're talking about. Let's see how that works out. There's nothing to solve. I mean, it's either infinity from one side or minus infinity to the other. There's no fix in that. You can, but what you do with it? I mean, you can factor it out, but you're still left with something. Yeah. I don't think it. I don't think it adds any additional like insight as to what's going on. This one, x goes to 2, right? What happens when we plug in 2? I get 4 minus 8 plus 4. I get 0 upstairs. What happens down here? 8 plus 20 minus 28. 0. Now this is the one that you're thinking about. This is type 0 over 0. And so that's where we want to do some algebra. And if our limit is x goes to 2, we want to factor out x minus 2 in this kind of situation. So can you guys help me out? How do we do that? I'm going to assume we can factor x minus 2 out of both of these. Now upstairs, I can just look at it and do it, right? Like that's x minus 2 times, well, x minus 2, right? Just plain old factoring, right? Can you see how to factor x minus 2 out of a cubic? Let me remind you, we have a technique for this. So if we take x cubed plus 5x squared minus 14x, and we want to divide x minus 2 out of it, we can use long division. And so that's x squared, x cubed minus 2x squared. We subtract those. We get 7x squared minus 14x. So I need to do plus 7x. That gives me 7x squared minus 14x. Remainder 0. Hooray, we're done. So what that shows me is that if I want to factor x minus 2 out, what's the cofactor to that? Well, it's x squared plus 7x. You're like, well, I wasn't taught long division. I was taught synthetic division. They did this box of numbers, and they did some kind of kabuki dance with putting numbers here and there and everywhere, and I don't really understand what we were doing, but I was taught this algorithm. Well, that's nice, but I can't help you with that. I don't know it. I don't use it. I use long division. So if you're a synthetic division person, my apologies, but I'm no help to you. So long division is more general because we can divide by a linear term, we can divide by a quadratic term, we can divide by a cubic term, you can divide by whatever you want. Synthetic division only works for linear factors. So I don't see the point. But anyway, now did you have to do this long division to see that factoring? I mean, I don't know. If I'd let you sit and stare at this problem for another 3 minutes, maybe you'd have seen how to factor it. I don't know. Maybe, right?
Sometimes
I wouldn't.
me, I don't know, but it's in my mind, I have to write it down. So
Oh, yeah, yeah.
sorry about that.
Oh, that's fine. No, I mean, that's... So then what? Right? Because x is not equal to 2 and the limit. So that cancellation is valid. And we're left the limit as x goes to 2 of x minus 2. And you guys like factoring, right? Factor out that x. You want to do that? Sure, why not? I mean, you can if you want to. But then the point is, at this point, we can evaluate the expression at the limit point. Right? Plug it in. 2 minus 2 over 2 times, well, 2 plus 7, right? Which is what? That's 0 over 28. Wait a minute. I can't do math. 2 times 9 is what? 18, not 28. What's wrong with me? Anyway, but 0 over 18, 0. So this time, 0 over 0, limited to 0. Is that good? Should we do? I think we should do more, right? So long division is a useful workaround if you forget how to, or if you just don't see how to factor something and it come up, Let's see if I can find another nice example for us. How about the limit as x goes to 1 of 1 minus the square root of x over 1 minus x. So what do you guys think we're going to do here? So what happens when we plug in 1? Yeah, it's type 0 over 0. Yep. So what does that mean? When we get type 0 over 0, what does that mean? That means we need to do algebra to remove the indeterminacy so that we can somehow cancel the zeros, right? And be left with something that we can either say, oh, after I remove the indeterminacy, it blows up. That could happen, right? Or after I remove the indeterminacy, it goes to 0. Or I think last time we had it go to fractions, right? I mean, it can do all kinds of different stuff. So this one here, the trick is to notice that 1 minus x is 1 minus the square root of x squared. Which means we can factor this as 1 minus root x times 1 plus root x. So this is my sort of algebraic thought. And so with that thought in mind, it's easy to see what to do, right? The limit try this again. The limit x goes to 1 of 1 minus root x over 1 minus root x times 1 plus root x. So we can cancel out the 0, right? We reduce the 1 minus 1 root x or 1 minus root x, and then what happens? Yeah, we've just got limit as x goes to 1 of 1 over 1 plus root x, and then now, well, listen to me, put it in 1 there, which is equal to what? 1 over 1 plus the square root of 1, otherwise known as 1/2. I plug in 1 because this expression is defined at 1. It's not like 1 over, and it's 1 over 2. I mean, when I plug in the 1, square root of 1 is 1.
So I'm just saying, in my mind, I'm thinking you got rid of this square root, you just added 1 plus 1.
Well, that's right, because the square root of 1 is 1. So